We're looking at a curve r equals 1 minus the sine of theta. We're going to find points where the tangent line to the curve is vertical or horizontal. Keep in mind that we have vertical tangent lines when dx d theta is equal to 0. We have horizontal tangent lines when dy d theta is equal to 0, but not both at the same time. Also, as a subtlety, we're asked to find points. These are going to be of the form r theta. It won't be sufficient just to give theta answers. All right, I'd like you to get working here. I want you to find dx d theta, set it equal to 0, solve the resulting equation, and do the same thing with dy d theta, set it equal to 0, solve the resulting equation, see if you can make sense of what you get, and see if you can find those points. In the event that you got stuck at all, if as I'm going through this, I unstuck you, then please repause the video and continue on with your work. X is r cosine theta, so x will be 1 minus the sine of theta, that quantity times the cosine of theta. Using the product rule there is going to give us that dx d theta is equal to negative cosine squared of theta minus the quantity of 1 minus sine of theta times the sine of theta. We end up with a negative cosine squared of theta, a linear negative sine of theta, and a positive sine squared of theta. We'd like this to be quadratic in terms only of one trig function, and so I'm using a Pythagorean identity to replace negative cosine squared of theta by sine squared of theta minus 1. I'll pause that for a moment and then move over to dy d theta. Y being r sine theta is going to be the quantity of 1 minus sine theta times the sine of theta. Again, using the product rule is going to give us dy d theta equals negative cosine theta times the sine of theta plus the quantity of 1 minus the sine of theta times the cosine of theta. Combining like terms, we have two factors of negative sine theta cosine theta, and so dy d theta then becomes negative 2 sine of theta cosine of theta plus the cosine of theta. Now let's see what happens when we set those expressions equal to 0 and solve the resulting equations. For dx d theta equals 0, we end up with, after we collect like terms, 2 sine squared of theta minus the sine of theta minus 1 is equal to 0, which then factors as 2 sine of theta plus 1 times the sine of theta minus 1 equals 0. Theta then equals pi over 2 from the sine of theta minus 1, and 7 pi over 6 and 11 pi over 6 when the sine of theta is equal to negative 1/2. Don't forget that we have to go all the way around the unit circle. For dy d theta equals 0, we factor out the factor of cosine. We end up with cosine of theta equals negative 2 times the sine of theta plus 1 equals 0. And I, for some reason, wrote these answers not in numerical order. Just a second. Okay, that's better. From the cosine of theta equals 0, we get theta equals pi over 2 or 3 pi over 2. For negative 2 sine of theta plus 1 equals 0, that would be the sine of theta equals 1/2. We get theta equals pi over 6 or 5 pi over 6. Now, if you haven't already computed the r values for these theta values, then I'm sure you can confirm that we have vertical tangents at 3/2 7 pi over 6 and 3/2 11 pi over 6. Remember, when we give ordered pairs in the polar coordinate system, we give r comma theta. And we have vertical tangent lines at 1/2 pi over 6, 1/2 5 pi over 6, and 2 3 pi over 2. We need to consider separately, though, pi over 2, because we got it as a result of setting dy d theta equal to 0 and also dx d theta equal to 0. I mixed up what I was pointing at, but you get the idea. We're going to examine separately when theta equals pi over 2. When theta equals pi over 2, we have that dy dx is equal to 0 over 0, which is an indeterminate form, so we need to deal with this using the L'Hopital's rule. I'm going to use the most convenient forms that I can think of for dx d theta and dy d theta because we're about to take derivatives, right? That L'Hopital's rule says to. So dx d theta I'm going to write as negative cosine of 2 theta minus the sine of theta. You can verify that's a representation using a double angle formula for the cosine function. And dy d theta, I'm going to use the cosine of theta minus minus the sine of 2 theta. And you can verify that based on using a double angle formula for the sine function. Dy dx then becomes the cosine of theta minus the sine of 2 theta divided by negative cosine of 2 theta minus the sine of theta. Now we already know that the result when theta equals pi over 2 is 0 over 0. So we're going to use, like I said, L'Hopital's rule. We're going to write this as a limit. The limit as theta approaches pi over 2 of the cosine of theta minus the sine of 2 theta divided by the negative cosine of 2 theta minus the sine of theta. Here's the thing though, folks. As theta approaches pi over 2, 2 theta approaches pi, of course. When theta approaches pi over 2, the sine of theta is positive from both the left and the right. No big deal there. But as theta approaches pi over 2, the cosine function is positive from the right, but negative from the left. And when I say right and left, I mean the unit circle. I really should be talking about as theta approaches pi over 2 from the minus side, cosine of theta is positive. But as theta approaches pi over 2 from the positive side, so angles greater than pi over 2, cosine of theta is negative. Now when we consider 2 theta going to pi, when we look at the cosine function, whether we approach pi from values less than pi or values greater than pi, the cosine function is negative. No big deal there. But we have that same deal with the sine function as we did earlier, and that is as theta approaches pi from the minus side, the sine of theta is positive, but as theta approaches pi from the positive side, so angles greater than pi, the sine of theta is negative. Therefore, I haven't written enough down here for our limit. We need to consider the limit as theta approaches pi over 2 from the minus side, and separately the limit as theta approaches pi over 2 from the positive side. Using L'Hopital's rule, we end up with the limit as theta approaches pi over 2 from the minus side of the negative sine of theta minus 2 times the cosine of 2 theta for the numerator, and then 2 times the sine of 2 theta minus the cosine of theta for the denominator. Evaluating this expression as theta approaches pi over 2 from the minus side now, sine of theta is going to approach 1, so in the numerator negative sine of theta approaches negative 1. Cosine of 2 theta as theta approaches pi over 2 from the minus side means the argument is approaching pi from the minus side, and the cosine of pi is negative 1. So we end up with, in the numerator, negative 1 minus 2 times negative 1. In the denominator, as theta approaches pi over 2 from the minus side, 2 theta approaches pi, so 2 times the sine of theta actually approaches 0 from the positive side. Remember, that's coming from the second quadrant. Minus the cosine of theta as theta approaches pi over 2 from the minus side is approaching 0 also from the positive side. Well, the numerator we see is basically negative 1 plus 2, so we have a positive numerator. The denominator, though, is still unknown because we have 0 minus 0 and, indeterminate form. However, we can deal with that by actually expressing the denominator factored. So I'm going to write this as 4 times the sine of theta times the cosine of theta minus the cosine of theta. Factor out the cosine of theta, we're left with 4 times the sine of theta minus 1, and then continue our analysis. As theta approaches pi over 2 from the minus side, the cosine of theta approaches 0 from the positive side. And the sine of theta approaches 1. So we end up with basically 0 from the positive side times 3. That results in a positive denominator. So what we have is a finite numerator and a zero denominator, both of which are on the positive side of the house. So I'm going to move this limit further, other one out of the way. And we end up with this limit is infinity, positive infinity. Now, a similar analysis will tell us for theta approaching pi over 2 from the positive side, using L'Hopital's rule, we are ultimately going to end up with a positive numerator and a negative denominator. So this second limit is negative infinity. Now let's go back to where we were way back up here. So if our tangent line has a slope of positive or negative infinity at theta equals pi over 2, that means we have a vertical tangent. So we can add to this pi over 2, which gives us a radius of 0, and we'll fix our answer just a little bit here. Slide this over, and we'll say we have vertical tangents at 1/2 pi over 6, 1/2 5 pi over 6, 0 pi over 2, and 2 3 pi over 2. How is all this working? Folks, this is the graph of a cardioid. And so at the pole, we should have a tangent line that has a positive slope of infinity and a tangent line that has a negative slope of infinity. I'm going to erase that because that looks pretty bad, but I think the visual helped a little bit. Anyway, this is our final answer. Took a bit of analysis at the end there. Hope it all made sense.